I'm missing a Dakota Duckett, a Todd Patrick, and an Eric Chen. Any of you here? Oh, look, there's a Dakota Duckett. Okay. Get my chat out. I actually have two screens now, so hopefully this is all going to work a lot better. Good morning, team. If you would like to unmask yourselves, that always makes my life more fun to see my students. Ooh, somebody has a beautiful picture in there still. You can put a fun still in. I should do that myself. Let me let you know that I have been having very bad technical issues. I have had my internet measuring basically 0.1 megabits per second. That seems to be back, but my computer crashed twice. We finish class each time. If I disappear, please stay in the meeting. I will get back up and then I pop back in. So just be warned, things might be a little unstable. What we are going to be looking at first is we are moving very fast because we are an AP course. And one of the things, the results of that means that we have to trim a few corners. So first off, I'm going to get to our presentation, which I believe is here. The first thing I want to explain to you is a unit that we're dropping is on overrun, data overrun and rounding errors. So what this is about is the idea that computers are not 100% accurate. Yes, that's what I said. Computers are not 100% accurate. It's a science thing. They are probably 99.999% accurate, but there are some functions that computers have that make them inherently a teeny bit inaccurate. To start with, there is rounding error. When a computer divides a number by a third, it is dividing by 0.3333333. It's dividing with a decimal. A third is a repeating decimal. Computers cannot use infinite strings to divide something. So the computer has a rule that it rounds off decimals to 3 places. So it will divide with 0.333. 0.333 is not 1/3. 0.333 and a third is a third. So when you use 0.333 to divide with, you are introducing a teeny bit of error. You are not quite as accurate as you could be if you were able to divide by 0.3333333 into infinity. That's pretty straightforward. So there is a teeny bit of error because computers round things off. You probably won't notice it, but if you're doing incredibly delicate calculations, it's something to remember and something you're going to need to know as a part of this course. The next one is called data overflow. Data overflow is the idea that certain computer systems can only handle so many digits. If you have more than that, they just go off the edge of the world. So say you asked me to present the number 1000 using an 8-bit binary system. I need 10 bits to represent 1000. If I only have 8 bits of that 10-bit number, that's all the information I'm going to have. Those extra 2 bits at the end, I'm never going to see because the machine could not capture that data. Think of it this way. The easy way is you're in a car. Your car's odometer, the thing that measures the miles you go, has 5 digits in it. It can measure up to 99,999 miles. When I go 1 more mile than that, what happens to the odometer? Somebody can tell me.
It does say that you went 10,000 miles on it?
No, it's going to go to 0. It's right. I only have 5 digits in my odometer. Right now, I'm in my car. I'm going along. It says 99,999. When I go 1 more mile, what happens to that odometer? You had it. Yes, it's going to roll over to 0, and I'm going to lose the 1 that's supposed to be telling me that I have 100,000 miles on my car, right? I can't get that 1 because I've only got 5 digits. But my car has 100,000 miles on it. But right now, my car is saying, the odometer is saying, it has no miles on it. So some systems in computers are like that. Like a byte, you've only got 8 bits in a byte. If you need to record a 10-bit number using an 8-bit byte, you're not going to get those last 2 bits. That is what data overrun is. It's when it goes over the limits of the system and you lose some data. So those are 2 ways computers can be inaccurate. Okay, into today's story. Today we are learning about representing text and creating black and white colors. So we are September 14th. We have a warm-up. We have a binary numbers worksheet review, which we are going to skip. Does anyone have a big problem with their binary number worksheet? Okay, we can talk about it on Thursday if you do, but I just wanted to see, I think everyone gets the basics of this. It's you get lost in the details of like, well, I can't go into it or I'll be giving it away. So then we're going to talk about representing text and black and white images. What are going to be due today is the warm-up you just did, the binary number worksheet, that's due today, and your Unit 1, Lesson 7 worksheet that we're going to be doing today in class for the most part. You might need to take it home and turn in the last piece of it. Our goal, you'll be able to understand how text is represented in computers and learn how binary numbers are used to make black and white images. Okay, let's talk over what did people get for the warm-up?
I got 1 byte is 8 bits.
Correct. That is fabulous. So we're just going back to what is a byte? A byte is 8 bits.
So 7 ones and the 0, the digit for that's 254.
Correct. And the way you know that is that first one in the 8th place, you know that's 128, and then that's everything included with it except for that the number 1. So it's going to be 1 less. Anybody get anything else? Anyone have any questions on that? Okay, so now we're going to get into representing data. This is the idea, like we did with our circles and squares, that you're going to need something to represent what something else is. We're going to be looking at a system called ASCII. This is another module that we've really reduced down to just ASCII for time. ASCII is the way the keyboard in your computer assigns a letter to a binary value. And so every key on your keyboard has a function. This is how those functions are mapped to the binary. You'll see, it'll make sense. Here we go.
Representing text. Hi class, how are you doing? What does that mean? I just wrote something down and those numbers appeared. What? Let's figure this out. There are a lot of 63s at the end of each of those lists of numbers. Hi class, how are you doing? There's 163 at the end of this set of numbers. and 363s at the end of this set of numbers. Maybe the number 63 has something to do with the letters above. There are 3 question marks at the end of the statement above and 363s with the numbers. Maybe the number 63 is a question mark? 63. Yes, we are going to introduce you to ASCII. ASCII, or the American Standard Code for Information Interchange. That's what it stands for, but everybody calls it ASCII. ASCII is a numerical code for each of the keys on the computer keyboard. It includes the shifted keys, uppercase, or percentage, dollar, asterisk, and lowercase, or 568. It also includes periods and commas, exclamation point. Each ASCII number from 0 to 126 is represented in a byte. Remember what a byte is? Oh yeah, a byte is 8 bits. Is a byte enough to represent the number 126 in binary? Yes! 111 is equal to 127.
We know that's not true. It's 255.
So here's a chart that can be used to convert ASCII into binary and what the character on the keyboard that represents. For the AP test, you will need to know what ASCII is, but you will not need to remember each number in the code. You should be able to use this reference sheet to decode some ASCII characters. We may have that as warm-ups for you in the future. But let's move on a little bit with ASCII. We're going to talk about abstraction. So if you type some text onto your cell phone, that text becomes ASCII. Each of the letters in the text, including the spaces, get converted into ASCII numbers. And each of those ASCII numbers is actually represented by binary code. We don't have to think about this layer when we send a text message, but every message that you send is really just zeros and ones. Abstraction is an important concept in computer science, and we'll talk about it later, especially when we get to programming. But what is another example of an abstraction from your everyday life? Something where you don't completely understand how it works, but you can still use it with confidence. Think about it. Your teacher will ask random students to answer.
Okay. Random students. Okay. Oh, I've got a big list now. Jessie Lynn, what's an example of an abstraction that you might use? Something you know how to use, but can't really say how exactly it operates.
Text messages.
Beautiful. Now, of course, you do understand how it operates, or you'll be more familiar. But that's perfect. Let's see, Julie Fawn. What's an abstraction that you use?
I guess like I could say because I wouldn't know that like actual complex machinery in it, but I do know how to use a microwave.
Exactly. Microwave's a great example. A car, any appliance, you know, a blender. I know how to turn it on and set the speeds, but I don't understand the gearing. I don't understand the linkages. That's all we're trying to get to. The idea that you do something, a whole lot of something happens, and then there's a result. I mean, somebody said video games. The idea that I click on the video game, I make my character go up and down, but I have no idea how all that imagery and interaction is being generated. So that's it.
Representing
Okay,
text.
hang on. We're not trying to go back into representing text. What I will go over quickly with you is this idea that you don't need to know ASCII for the AP test, but you may be given, oh, come on. You may be given something like this key and a string of numbers and told that you need to translate it. So 98 is lowercase b. It's 01100010. That's 98. 100 is lowercase d. 35 is the pound sign. So like your flippy-do, this is just a key to how to interpret ASCII. You may be given some series of number strings like we were showing you before. What's really cool about the way they started this is like the Rosetta Stone. This is how they figured out how to translate ancient Egyptian hieroglyphics, because they had a stone that had ancient Egyptian written and Greek and something else. And between those three languages, they were able to figure out what those Egyptian hieroglyphics were. Uh-oh. Let me see. I think somebody, hey! People waiting outside. Okay. You're supposed to. Okay. So now we are going to get into the more fun part of this. We did our abstraction. Unit 1, Lesson 7. So you're going to need to go into code.org for this. You also need to download a copy of your worksheet. So this is the module. Here's the activity guide. These are both actually ways to get to the worksheet. What you want to do when it opens up is you want to make a copy of it or download the activity guide. If you want to go in and make a copy, it's this other link. You click this, you click on document. There's the Google Doc, and now you can make a copy. Add, make copy. Okay. You want to be going into your code.org. Let me get back out of here. So when I go to code.org, it offers me to view my course. I want to view my course. We want to go down. We're in Unit 1, Lesson 7, black and white images. The first thing we're going to be going into is 3. But we're going to watch a little video first, okay? All right, so let's go up to presenting. Well, first, actually, this is a fun one. You recently did some online shopping and are expecting a package to arrive in about a month. The delivery service has a tracking system which reads the location of the package. How often do you want the location read? Every week, every day, every hour, every minute? You guys can just sing out, what do you think is what you would want? Your package isn't going to come for a month. How many times a day or week do you want to get a notice about where it is? Oh, be brave. I can ask people.
Day.
Just throw out an answer. You had it.
Day.
So every day. You'd like to get an update every day. Somebody else, Taylor Branch. When would you like to get notified about your month-long package?
Every week.
Every week. Anybody else have a different opinion? Ethan Z, when do you want to be notified? Ethan, you in there?
Yeah, hello.
All right. There's no wrong answer.
Um,
If it's a month out, how many notices do you want to get?
I would read.
Okay. If it's a week out, how many notices would you like to get?
A day.
Once a day. Let's say Seth Goldfine, the package is a week out. How many notices would you like to get?
I might go every other day.
Every other day? Somebody else have an idea? Kyle too?
I'm with the day.
Okay. Now you really need your package and it's 2 days out. It's film that's coming and you have to upload it to NBC. How many notices do you want to get a day? Or how many notices do you want to get, period?
1 every 4 hours.
1 every 4 hours. Who else?
An hour.
An hour. Why are we reducing the time period for when we want our notices? When the package is far away, we don't really care. So it's okay to look at things in big blocks like a week. I know it left China. I got no idea where it is. I know that it made it to the US, but I'm not sure where it is. The more samples we take of that timeline, if I get a notice every day, if I get a notice every hour, if I get a notice every minute, it's making the resolution of where my package is much greater. If I have it every day, I know where it's beginning the day and ending the day. If I have it every hour, I know when it's in the facility or it's on the truck. If I get one every minute, I might know like what street the truck is on. So the idea that we're trying to get in your mind is the more samples you have, like the difference between getting a notice every week or a notice every minute. So once a week, you're getting 1 notice. Once a minute, you're getting 60 notices an hour. Times 20 is 120 times 4. You're getting 144 messages a day about that package. So you are getting a lot more information. You are seeing much more clearly what is going on. This all relates to the image drawing that we're going to be doing. Okay, black and white images. Here's our fabulous video.
My name's Lydia Choi. I work for Oculus as a technical art director, and I'm currently working on virtual reality hardware. Kind of like a baseball cap. So it's kind of like this motion, and then you flip down the current thing that we're building is a virtual reality sculpting tool, trying to simulate like clay sculpting in space. Welcome to the pixelation widget, where you will encode a black and white image by typing out the binary yourself. Don't worry, it's easier and more fun than you might think. In this widget, the first 2 bytes, 16 bits of data, are used to define the width and height of the image you want to encode. The first 8 bits define the width and the second 8 bits the height. You have to type out all the bits, but the widget shows you the decimal translation so you can make sure you're typing the numbers you want. To make it easier to keep track of where you're typing, you can add spaces and line breaks to the binary code. The widget doesn't pay attention to them, it just interprets the bits that are there. And now it's easier for me to see which bits I need to change to set the width and height I want. I'm going to make a very small image that's just 4 pixels by 4 pixels. Now the fun part. After we've set the width and height of the image, the next bits we type are the bits that define how the pixels are colored. We're just working in black and white for now, so keep it simple, 1 bit per pixel. In digital images, we define color in terms of light, and we can turn the lights behind each pixel on or off. So we let a 1 mean turn the light on, which gives us white. A 0 means turn the light off, which gives us black. Did you notice that I added line breaks when I was typing so that I could keep track of the row I was working on? That's a handy trick, and we actually have buttons that will help you with that. If you click the raw format button, it will strip out all the spaces and line breaks so you can see what the raw binary code looks like. The readable format button will reinsert spaces and line breaks to make it easier to read and edit. If you screw up your spacing or get lost in the bits, you can always hit format and it will clean things up for you. Let's look at an example of a bigger black and white image. If you click actual size, it will show you what your image looks like when using the real pixels on your computer. For images here, it's probably going to be pretty small. Lastly, you can save the wonderful image you've made by clicking Save PNG. This will take the current state of your canvas, whether you're zoomed in or showing actual size, and pop into a new window. You can drag the image from there to your computer or save it in some other way.
Okay. All right, team. No, no, we don't want that. Next. Okay, pixelation widget. So is everyone able to get into code.org? Is anyone not able to get into code.org? Thank you, Kaylin. Okay, so right now I'm in code.org. I am presenting for you, and we are going to go to 3, pixelation widget, black and white. Okay? When you click on 3, you're going to get this, puzzle 3 of 10. What I think makes sense is if you open another window in code.org right next to you and go down to lesson 7 and click on lesson 3, you're going to keep this because once you go into the lesson, you lose this image. I've been saying you can take an image grab, but this seems like the best way to do it. So once I'm in here, I'm going to go into my widget maker, my pixel maker. But now I've forgotten what my A looks like. Oh gosh, how did that A start? I can't remember. Instead of going backwards, I can just click right next door. Oh, there's my A. What's the best way to do this? You look at the top row. What are the color schemes? White, black, white. Okay? Given what she told us, what do I need to type in here to make white, black, white? Seth Goldfein, what do I need to type? Save me.
Would it be 101?
101. Look at that. 1 is light on, 0 is light off. Then I'm like, but what's the next part? Okay, I go back. Oh, look, it's going to be dark, light, dark. So what's our next bit of code? Come on, somebody be brave. Dark, light, dark.
010.
010. Okay, that's it. That's all it takes. But it really helps to be able to reference your image. That was my biggest problem. I kept forgetting what my image looked like while I was trying to make it. So this should be easy. Okay, get started on this one. If you get done with this, you can go on to 4. 4 is going to be this image C, although it's not going to look like this for you. Something is going to be wrong in the coding. I'll give you a secret. Look at your image, look at your code. Somehow these numbers are going to be a little off. And you can see it, same thing. White, black, 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 white. Oh, gee, that's a 1, a million zeros, and a 1. All these are black. Oh, all those are black. You'll see the pattern, okay? So let's take about 4 minutes, 5 minutes. I'll touch base with everyone at about 2:17. See how we're doing, okay? If you're having trouble, you can always ask me. or you can text.
Wait, do we move on to the fourth one?
Yes, you can move on to 4. You can even move on to 5, but 5 takes a little explanation, but it's not going to hurt you.
After 4, should we move on to 5 or wait?
You can, like I say, you can move on to 5, but it takes a little explaining.
Okay.
It's pretty straightforward, though. You're not going to hurt anything trying to do it. So go ahead and read the instructions and jump in. Okay.
The A has to be black.
Has anyone not finished number 3? Anybody not finished with 3?
0, 1, 0, 1, 0, 0, 1, 0.
And let's go to 4.
0, 0, 1, 0, 0, 1.
So you got to mute yourself. We're hearing you counting your zeros and ones. It's a popular thing to do. So for number 4, is everyone finished with number 4? Have they figured out how to get their C back to looking like a C? Julie Fawn gives a thumbs up. Yay, Julie. Everybody else, is there anyone who has not finished 4?
I'm not finished.
Okay. Four can be a little tricky. I think the advice they give you is hunt down the extra bit and remove it to fix the code.org logo. 1 bit early on would make it look like many bits were out of order. That's the secret. Says a single extra bit was inserted into the stream of bits that makes up the C in the code.org logo. That extra bit bumps all the other bits down the line, which makes the logo look messed up. Hunt down the extra bit, remove it to fix, or 1 bit early could make the whole thing look weird. Okay, I'm going to move on. You can keep working, but I'm just going to explain what we're going to be doing in 5. So for 5, you need your worksheet. You need this activity guide. You need to have downloaded it out of the module. Okay, we are going to be building a digital image. Work to digitally represent the image below. Read each square in the image and fill in the responses on the worksheet. Enter the bits in Code Studio and use a timer to keep track of how long it takes. Remember, each bit can only be either black or white. You will have to decide for each square. So here we are. We've got our, this is in theory a swan or a goose. We are going to have to turn each one of these squares either on or off to try and make this image. What do we do when we get here? Like pixel 4 in the top row. What do I say? I mean, pixel 3 is almost harder. What do I pick? Do I pick white or black?
8 by 6.
What's your thought?
Black.
Black. Why not? Now, I am assuming that he's basing that on the idea that more than half of this image is black. More than half of this one is black. A little less than half is black in this one. This one, I don't know. So you're going to have to make your own judgments. And that's going to come to the end here. We're going to ask you, when finished sampling, how many total bits were needed? How do you measure how many bits are in a picture? Somebody should know this. How many squares are in this picture? How do I calculate that?
Well, it's 6 by 8, so we know it's
6 by
48.
8, length times width. Same thing on a TV screen. 1080 is 1,080 lines of resolution by 1910, I believe. How long did it take you to build this? Try and keep that in your mind. You know, did it take you a minute? Did it take you 4 minutes? How much does the digital image resemble this one? Why might that be the case? Okay, so
1 0 1 1 0.
get into your code.org. I've got this one open, so I'm going to go to 5, and I'm going to make, you know, whatever I want right here. I make my 6 by 8. You want your canvas to be the same size
1 0 0 0
as the other one. Okay, so do 5, and if you get done with 5, you can go to 6. Work to digitally represent the image using sampling, reference your activity guide. What's different with 6 from 5?
0 0 1 1 0 0.
Here, I'll let everyone work on this, and then I'm going to ask what the difference is. Let's take about 4 minutes. You've got till 2:24. Try and get through 5.
0 1 1 1 1.
You're not muted.
I can fix that.
Zero.
I swear.
1 0 0 0 0 1.
The guy that's, yeah.
Problem solved. Thank you for singing out.
Mr. Swift, what should we use? What should we make the width and the height of the image?
For 5?
Yeah.
Okay, I think you can see my screen. You just got to count the squares on the image. So this is 1, 2, 3, 4, 5, 6, 7, 8 high, and 1, 2, 3, 4, 5, 6 wide. There's no technique. You just have to go in and physically count them to make sure you're using the same size grid. Okay, so it's going to be 6 wide and 8 high.
Okay, thank you.
So then when you get to this one, you're going to have to count for 6. 1, 2, 3, 4, 5.
12 times 16.
16. And then 1, 2, 3, 4, 5, 7, 8, 9, 10, 11, 12. Okay. That part you just sort of have to do manually to make sure that you're getting it right. Okay, let's go back to my favorite question. Is everybody done with 5? Has everybody managed to complete 5?
No, Mr. Swift,
Yes.
I'm kind of confused on 5.
Okay.
Because like
What's
I don't
that?
understand. Like the one box has white and black in it. I don't understand how to do that.
You just have to pick one or the other. Like I say, you're basically trying to gauge, is it more than 50% black or less than 50% black? If it's more than 50%, you make it black. If it's less, you make it white. If it's 50-50, nobody cares. Make it black or white. There's no right answer. Everyone is going to make their swan a little differently because you're all guesstimating, is that more or less than half white?
All right, thanks.
Just have confidence and just throw them out there. Okay, so I'm going to now ask a question from the sheet. So we figured out that we are using how many bits here? How many bits were needed to make this guy, which is 6 by 8?
48.
48, perfect. How long did it take to build? I'm guessing a couple minutes.
About 5 minutes.
Okay.
Less.
So that's fine. Just keep that as like a marker. We'll go back to it when we do the next one. How much does the digital image resemble this one? Why might that be the case? Who wants to take that one on? Anna? Anna Solis Garcia de Parada? My favorite name.
What? Sorry, I was doing the thing.
That's all right. How much does the digital image in 5 that you made resemble the beautiful goose or swan in this one?
Almost nothing.
Right, it looks nothing like it. But why?
Because it's just like a block of.
What is it about the package being delivered and how many times we want to get the report? What's wrong with our sampling technique to make this look like a goose?
Yeah.
Sorry, you got it. What's the problem with getting only a report every week about your package?
Wait, what?
It's the idea, I'll let you off the hook. It's the idea that the squares are too big. We don't have a very fine sample. We're using big blocks. We're looking at weeks here. So when we chunk 1 week white, 1 week black, we're covering a lot of in-betweens there. So it doesn't look a lot like the image, but it kind of can resemble it. You know, it looks like something, but that's all, okay? So that's all we're trying to learn from A. Go ahead and start doing B. B, it's the exact same process. How many bits were needed? How long did it take to build? How does the new image compare with the one from challenge A? What effect did taking a larger number of samples have on the image? I think you guys already know the answers to these, but go ahead and create your swan.
What are we supposed to do on 7?
7, just wait. I'll explain, but people need to pay attention. Don't worry. Basically, you need to find a logo that you want to create. Hint, find a simple logo. Okay, how's everyone doing on B? Is there anyone who hasn't finished their Swan B?
I'm not done yet.
Okay. No worries. Is it a swan? Is it a goose? Okay. Somebody who's finished their challenge B, let's go through our answers here on the worksheet. How many total bits were needed?
129. Sorry, 120, 192.
Good job.
Jesus
Somebody must have
Christ.
a calculator. Okay. And that's just the idea that we're doing height times width. That is how television is measured. Normal television is 525 lines of resolution. 720 is 720 lines of resolution by 1080. 1080 is 1080 by 1910, I think. Those are ways of measuring resolution. The bigger the numbers, the greater the resolution. 4K, 4,000 lines with something. It's just terrible. Imagine picking all those things up. How long did it take to build Challenge B? I think
Not
that,
too long, like
not too long.
6 to 8 minutes.
Okay, so 6 to 8 minutes, and Challenge 1 took only 5 minutes or 4 minutes. Why is Challenge B taking longer?
Because you have more stuff to fill in.
Exactly. You're using a higher sampling rate, so you have a lot more little boxes to fill in. Also, Challenge A took longer because you'd never done it before. Once you've done it, it's not quite as hard to redo everything, but you've got probably 3 times more boxes in Challenge B than you do in Challenge A. I mean, that's an amazing thing with TV resolutions. Do you know that a 720 HD image versus a 1080 image, a 1080 image has 9 times more information in it than a 720 image? Okay, so this is the big challenge. If we can get this, I doubt you'll be able to get this done in class, but we can try. You are going to need to create a grid. If you can print out one of these grids, that's fine. You might need to just create it doing something silly like what I did. Hang on, I am presenting, aren't I? Yes. All I did was I took my paper and I drew lines down to make boxes like graph paper. You need to select your favorite company logo, decide how you're going to sample this logo. Use one of the grid sizes below. So these grids, I'm calling them, it's a coarse grid, a medium grid, a fine grid, and an extra fine grid. So depending on your logo, it might be very easy or it might be very difficult to represent it in a coarse grid and have someone recognize it. It's like your first goose. So you're probably going to need to be working in either the fine or very fine, because someone is supposed to be able to identify your logo. So then copy the image. Okay, copy the image you make on the code.org widget in Circle 7 to this sheet. To copy, you can print with your computer screen and then crop the image using the crop tool at the top. Okay, so basically you need a grid to start with, and you are gonna hand draw your logo on here. So my feeble attempt here is drawing like a Nike swoosh over top of my grid. Once you have that, you're going to do the exact same thing we just did with the swan. You're going to say, you know, white, 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 white. Is that enough black to make it black? No, white. Maybe this one can be black. That one can be black. That one, no. This one, black, 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 and then white, 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 white. So you're trying to create a logo with your pixel maker that somebody could recognize. Oh, help, somebody's in the waiting room.
When we do this, do we just submit it online, or do we need to upload it somewhere else, or can we just submit it through code?
No, it should go in the same place as you're going to be submitting your worksheet.
All right, awesome, thank you.
So ideally, it's just going into a Google thing.
Wait, I'm confused on how to get it on the doc.
Okay, you cannot make it on the doc. Well, you could. If you're, well, you'd have to use Google Draw, or you'd have to scan it or something. The idea is you're just going to make a piece of paper with your graph on it, or you could print out this and use one of those to draw your logo on top of. Once you have that, you're then going to go to, so when I'm in 5, when I'm in 7 tells me select your favorite company image, decide how you're going to sample the logo using one of the grids from the activity guide, draw the logo, recreate the logo on this level, show the logo to a classmate, make adjustments as needed. For example, you may need to increase the sampling in order for the logo to be recognizable. You want your logo to be recognizable. So you're going to have a drawing on a grid, just like the goose or the swan. Then you're going to need to make your thing. Okay, I'm making, mine is going to be 20 by 30. So mine is going to be 20 high by 30 wide. Oh, that's height. So let's go 20 high by 30 wide. Okay. Then I'm just going to look at my grid, and the way, you know, that piece of paper that I was looking at had it. It had, so I know I've got 30 across the top that are going to be white. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Return another 30 across the top that are white. Then maybe it's, you know, a black. And then, you know, more white. That's how you're going to build it. You're going to look at your grid, and you're going to need to do exactly what we've been doing with the goose with your logo that you drew on there. Does that all make sense?
Mr. Swift?
Yes.
We're done with 7 on code.org. Should we go to 8 or just submit our picture?
There. Yes, I want you to ideally, you're going to need to finish the module for your homework.
So you want us to go all the way up to and finish question 10, correct?
Yes.
Okay.
When is this due?
It's due next class, next Thursday.
Wait, so is the last box that we have 22 by 22? Am I counting correctly?
What do you mean?
So we have to create a company logo in 4 different formats.
No, you don't.
The first is 5 by 5, 8 by 8.
No,
you don't have to do that?
You are not doing 4 logos. You are doing one logo.
Right. Amongst 4 different.
It is up to you to pick the grid that you want to use for it.
Oh, so we don't have to do one for each of them?
No.
Oh, okay.
We're not trying to make a lot of work.
I'm overthinking it. Yeah, I think, okay. Thank you.
All we're trying to go to it's your worksheet that has the grids.
So I thought we just needed to do one of each. Okay.
No.
Thank you.
You need to pick what is your, because you know it's going to take you longer to work with the very fine grid than the easy grid. But you need to have the logo be recognizable. So that's why you're probably going to need to use the fine or the very fine to do that. And that still may not be fine enough. And you can adjust your widget in the thing, but just try and make it so that it's recognizable. That's all. Okay. All right, we have 1 minute left in class. Any questions? Anyone having trouble? Does it make sense that we'll just finish out this unit? Everyone is diligently working away. So pixel data is, assume your friends just sent you a 32 bits of pixel data, just zeros and ones for black and white. We're encoded sampling an image. Choose the 2 statements that are true. The 32 bits of pixel data is enough to produce an image using the widget. Nothing else is needed. Digital image would be the exact size of the analog image. Oh, I know what, shoot, we didn't get to. Sorry, let's go to present. Okay, so metadata. Metadata is data that contains information about data. The first 2 bytes of data for each image give data about what is in the file. We call that metadata. For the images you are making from the widget, the metadata describes the number of squares horizontally and vertically. All this is saying is that analog data produces smooth edges, smooth corners. Digital data starts and stops. So it does not make smooth lines, it makes pixelated lines. It doesn't make a smooth music arc. It goes up in stair steps, but it can sound very similar. So take a look at this. If the end of the lecture doesn't make sense, just getting the worksheet in is really all we need to do. Okay, you are free to go.
Thank you.
Thank you.
Thank you.
Thank you. It was a great day. I think we learned a lot.
Thank you.
Thank you.
Swift, I had a question.
Sure, absolutely. I'll be here for anyone who does too.
Yeah.
What if you wanted to do like a logo that is like less known, like a logo that not many people would know?
You can do whatever you would like. The idea that somebody's not going to be able to identify it, I don't think that's going to be counted for points.
Okay.
But ideally, bear in mind, you want the simplest logo you can possibly find.
Got it.
Because you're just trying to do an exercise to show how you would take something, put it on a grid, and represent it using pixels. So things like that code.org that's actually made out of big blocky pixels is an easy choice.
Okay.
But make your life easy.
All right. All right. Thank you. See ya.
Mr. Swift, should
Yes.
we submit the worksheet?
Yes. You submit the worksheet, and it sounds like you'd be submitting the image of your final project. But I think you're doing that in the widget too. I would think that would get captured.
Yeah, I haven't printed out the worksheet,
Okay.
so I couldn't like draw it on there.
Okay. Well, like I say, you can just take a pen and make the lines of your paper into a grid.
Yeah.
You're just trying to write down, you're trying to draw your logo on a grid in a way that you can then start going into the pixel maker and go white, white, black, black, white, black, white, white,
Yeah.
white. That's all you're doing.
Okay, thank you.
No worries. Anybody else? Questions?
So are we copying and pasting our logo onto this worksheet?
No, you have to draw it. You just have to pick one of those grids that you think will let you make your pixels in a way that you can actually recognize your logo.
Oh, so we're not.
Like I say,
talking-
I thought, gee, Nike swoosh, that seems pretty easy. So I made my grid by drawing down lines across there. And then I just tried to draw it on here. And so then, you know, it's going to be white, 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 you know, white, black, black, white, you know, white, black, 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 white. It's not going to look much like a swoosh at that resolution. If I made my grid finer, I could probably make it recognizable. Does that make sense?
Yeah.
But you're just drawing it on as an outline so you can see how your pixels should be allocated. White, black, white, black, white, black. That's all you're doing. It's going to end up being the exact same thing as your goose. It's going to be a picture with a grid over it, and then you're just going to ID white versus black.
Okay, thank you.
Not a problem. My pleasure. Anybody else?